The first question is derive the three-dimensional heat diffusion equation for Cartesian coordinates with volumetric heat generation. Oops. So what I have started here is just a couple diagrams. So on this cube here we have our control volumes of dz, dx, and dy. And over here I just drew one heat flux. So we're gonna have on this side we're gonna have our heat flux as qx, and then once it reaches the other face on the other side of the axes, it's going to be our heat flux of qx plus dx, insinuating that this length is going to be dx. Okay, cool. And then we're going to derive our conservation of energy equation using our heat flux values. Okay, now to do the conservation of energy. So what we're going to have is, let's draw it over here. So we're going to have our energy accumulated is going to be equal to our qx minus kind of what we're doing up here. I'm just using caps so it's easier. And then it's going to be, I might have to move it over. We might not have enough room. So we're going to do all the faces to get the whole accumulation plus dy. And then I'll just go write it down here. Plus if we generated any heat during this time. So I'm just going to move this over. So that's our conservation of energy equation. And then what we can do with this is Taylor expand it. Excuse me. So what we're gonna get after we do a Taylor expansion, we're gonna expand the x dx, and we're just gonna assume this is the same for all sides because it will be. So once we get an expansion, we're gonna get qx plus differential qx over differential x plus, or not plus dx, just dx, and that's what we're gonna get. And once you kind of do some what's it called, like once you move around these, you'll just realize that this quantity here is going to be equal to that, but just negative. So this can be kind of substituted as negative differential of our heat flux over differential x dx. So yep, that will be equal to that on all sides too, because they're all equivalent. So then what we can do after that is we can kind of start working with our Fourier's law stuff. And let me just write down Fourier's law, just so it's on the screen. Let me do an arrow, not an equals, because we're going to do an equals right away. And we're going to have k, negative k, of course, dt. Okay, there's our Fourier's law. So what we're going to do now is kind of just add it in to, let me make sure this, okay, kind of just add it into our already preset equation. So let me add another page. What we're going to have here, we're going to have negative differential. Okay, so all I'm doing here is kind of taking this qx and this qx here. Let me use the laser pointer. And since it's here, I'm just gonna substitute this value for qx here. Yeah, basically that's it. Our area in this circumstance, once you look up at the cube, is going to be dy dx, or sorry, dy dz. And then the differential, just re-add that. dx, of course, because you can't forget this value. Okay, that looks good. And then this can just be simplified to okay, awesome. So now what we're gonna do is just add everything together. Add everything together and simplify. Seeing if I can fit this all on one page, because that would be awesome if I could. Let's just move 4 years all up here because it's not that important. Oops. Hopefully that's still recording. Okay, cool. Oh, that's my D. I think that's from over here. Okay. Now we're just gonna combine. Can you still see my pen? Okay. Now we're just gonna combine stuff and cancel. So, I'm just reminding myself quickly. Okay. So we're gonna have row C, and then we're gonna have that value that we just found. Oh my gosh, it is extremely windy right now. And then we're just gonna add this value here, keep circling with my hand like you can read it. But for all the different faces, so we're gonna have d squared t over dx. And we're just gonna do this for all of them. Okay, and then we're gonna multiply by our volume again. And then finally we gotta multiply by our heat flux, which is also multiplied by volume once again. And once even writing this out, you can see we're gonna have cancellations. So we can see that this will go to 0, like all of these volumes will. And then this value here can be divided on this side. So we're gonna get that, which is alpha, and then we're gonna get over the Q2, right? Yeah, those are only two quantities on the right hand side. So our final is gonna be dt dx is equal to alpha, or thermal diffusivity, d squared t over dx. Do it all. Okay. Awesome. So that was deriving the three-dimensional heat diffusion equation for Cartesian coordinates with volumetric heat generation. So now what we're going to kind of do is use this equation and also the one-dimensional heat diffusion equation to answer these next three. On to part A, question 2, which is for one-dimensional heat diffusion with heat generation where one side's insulated. Derive an expression for the temperature profile and sketch. Explain physically why the magnitude of the temperature gradient increases further. Okay, so I got us started here with the insulated wall at x equals 0, where the insulation ends, and x equals L to the desired length. And then I have the temperature profile, the temperature at the surface at the top, and the bottom undescribed. So, oops, okay. I have our starting equation here, which is just the heat gradient mainly, and then we have it equaling 0 because this is a steady state equation. So the first thing we're going to do is we are going to integrate our starting equation. So when we integrate this equation, we're just going to get dt dx equals q over kx, and then our constant of integration. So now what we need to do is find our c1. So to do that, we need this gradient up here that I wrote out is going to basically describe like c1 is 0, because once you solve it, it's just going to equal 0. So we don't have to worry about that right now. That's pretty common. So we're going to integrate it once more, this time using our other boundary condition. Let's move down one so we have enough space. So using that boundary condition, we're going to get just integrating quick. So we're going to get C2 this time. After integrating using the other boundary condition. So now what we're going to do is exactly as above and try to find C2, which is not going to be as easy as C1, but it's okay. Okay, let's just get started. So we're going to have TS that would stay the same. And we're going to have L squared. Oh yeah, this is for TL, TS. And then C2. And then just get the C2 on the right side. So we'll have TS plus Q over 2K L squared plus C2, or equals C2, geez. So we did find our C2, but we still need to add that into our C2 equation, so let's just rewrite everything. Okay. So we got that. Now what we can do is, since these two are constant, we can pull the x squared and the L out. So then what we're going to get is going to be Tx. Let's write the Ts first so it's not as confusing. Then Q 2K, and then we're going to have L squared minus, because of the negative x squared. Is that right? Yeah, I think that is right. Okay, cool. So, oh my gosh, as soon as I look up every time. What we're gonna have here now is, since we have an x squared, that's going to show, it's gonna make a concave down. So I can kind of show that up here. So let's say I have like our starting here, and we'll just end at the axis, why not? So what we're gonna do is have a concave down, but it's important that we don't like rise at all and then come down, because that would be a different kind, that would be if there was no insulation. So we're gonna have just concave down like that, instead of like, say, straight linear like that. Awesome. Okay, I think that answered our question. Let me make sure. Yeah. Explain why, physically why. Oh, explain physically. Okay, I can do that. So the reason why this is concave down is just due to the buildup of heat. So The reason why this isn't linear is because heat just keeps building and building and building and building, which just keeps pushing these like further down and further down, and then it creates this slightly concave. So yeah, that's kind of explains our that's okay. Kind of explains our heat and how that works, and how we use the one-dimensional heat equation to sketch a profile. Okay, on to number 3. Let's write a 3 here, and we'll just move straight on. So question 3 is simplify A1 for the case of steady state 2D heat diffusion with no heat generation. Apply finite difference approximations and derive an expression for the relationship in temperature between adjacent nodes. Okay, so simplify A1. So so we're gonna have to simplify this equation for steady state 2D. Okay, cool.
Okay, I just wrote down 3 equations for question 3, which are basically just already what's stated, which is steady state and no generation equations. And then, using this equation that we derived above, we're gonna solve for everything else. That's weird. So we're going to make a matrix similar to what we've done before. A 2D matrix, that is. And we're going to call this middle point just TP for target point. And let's call them up, down, right, and left. And so, using that equation, it's a quick recording, okay. Using the equation that we have up top, we're going to get right minus 2 TP plus left over delta. Oh, let me add this. This should be delta squared, but the way we get delta squared will be, so this will be our delta x, and this will be our delta y. And they'll just equal delta together. So what we're doing is we're multiplying delta times delta in the denominator, so that's what we're going to end up getting. And then we're just going to do exactly the same for the y coordinates. Oops. Up, right, left, down. For delta. And then we can combine these terms together. So we're going to get, because we gotta have them equal 0 at the top here. So we're just going to substitute this in for this, and this, and for this, and then equal 0. So I'm not even gonna bother rewriting it. I'm actually just gonna take these, and we'll add them together. Equals 0, correct? Yes. Okay, cool. And finally, what we can do is solve for TP. So what we'll get is we'll get TP equals TR, TL, TU, TD, and then that's going to be all over delta squared. So what this is kind of showing is mainly just an average, no matter where you are in the matrix, it's just going to be an average of the temperature. So what I'm going to do now for question 4 is kind of explain that in Excel, and I'll do that as soon as I get the Excel file set up.
Okay, I'm having slight problems screen recording. So I'm just going to do it this way. Sorry, I'm trying to fix the camera. Okay, that looks good. Okay, so I set up our matrix here, and on our left-hand side we have 100, right-hand side 200, top 310, and bottom we have 250. So what we're going to do now is we're just going to add the formula that we just made in part 3 to the XL, which is all our values around the target point divided by 4. And then we're just going to drag it on over and drag it down. Okay, there you go. And that just shows our matrices and how there is a different value for every matrix in, or for every cell in the matrix.